So we're going to continue talking about the cardiovascular system, specifically with mean arterial pressure. So our objectives for today are as follows. Okay, so we're going to talk about what affects cardiovascular, or what affects mean arterial pressure, the differences between systolic and diastolic blood pressure. There's no reason why that S should be bolded. And then just how this changes and how this is controlled. And yes, it's almost guaranteed there will be a question on either this, on the Unit 2 exam or the final exam, asking what causes diastolic blood pressure. So, pressure. With systolic blood pressure, remember, this is the pressure, the greatest pressure that's in the arteries, okay? And this is caused by the ventricle contracting, right? So just imagine you put a water balloon on, like a spigot on the hose, and you turn that on full blast. What happens to the water balloon? It expands out and it fills up really fast. Systolic blood pressure is affected by both heart rate and stroke volume, and that's important to know. And we're actually going to be doing some worksheets in class that you may or may not remember from 220 that are related to this. Then we've got diastolic blood pressure. Now, this is the minimum pressure in the arteries. This occurs during ventricular relaxation, but notice that it's caused by the elastic recoil of the arteries. Okay, so just imagine that, whoops, sorry, I was wondering where that went. Remember that balloon that we filled up? Well, what happens if we take it off the spigot and let go of the end that we filled up? Well, the water will come out of the water balloon because of that elastic recoil. And this is affected by the resistance, okay? And remember, resistance is most affected by radius, okay? And so diastolic blood pressure and total peripheral resistance are related to each other. Now, total peripheral resistance, like, good segue here, is the resistance to blood flow throughout the entire circulatory system. That's why it's called total peripheral, okay? And we're not really talking about the pulmonary vasculature. So if we decrease the radius of the blood vessels, that's vasoconstriction. If we increase it, that's vasodilation. Okay, but radius is the important part of this. It's radius that causes, or that has the greatest effect on resistance. So a few more definitions, and really this should be review. So we've got cardiac output, which is just how much blood leaves the heart every minute. Mean arterial pressure, which is the average pressure in the arteries. And there's a couple ways to calculate it. 1/3 systolic plus 2/3 diastolic. In theory, you can calculate it by going heart rate times stroke volume times total peripheral resistance. But there's no actual way to measure total peripheral resistance. Okay, so if I give that to you, that's one thing. But it's not something we can directly measure because you'd have to know the resistance all throughout the body. And we just don't have, as far as I am aware, the ability to do that. Okay, so I want you to look at this figure for a second and just look how pressure changes as we go throughout the circulatory system. So notice that we start here in the left ventricle. So as soon as blood leaves the ventricle, goes into the aorta. And then we've got these large veins. Okay, that's like the vena cava. Notice that we have big pressure fluctuations in the ventricle. So that's these first few lines. In the arteries, though, we don't relax as much. Okay, so here's your 120/80, and that's all to do with the arteries. But as we go down in size, from the arterioles down to the capillaries, pressure is pretty constant. There's not really a big fluctuation. Obviously, there's going to be slight, but nothing huge like there is in the ventricle or the arteries. And by the time blood returns back to your right atrium, there's almost no pressure. Your heart contracts just hard enough to get that blood back to your heart. Doesn't push any harder than it needs to, right? We're trying to be efficient. Now we're going to talk a little bit about blood flow here, and we're going to talk about how exercise affects blood flow. So for right now, I just want you to focus on the bottom half, so right here. Okay, so cardiac output, normally about 5 liters a minute. Notice where all of the blood flow is going. So here, we call this the splanchnic region. It's kind of a fun word to say, but just think digestive system, internal organs. Okay, so about 20 to 25% goes there. 4 to 5% goes to your heart. 20% goes to your kidneys. And then, just you kind of see it. And then the other one I think is kind of important, just because we're talking about exercise here, is the muscle, and then also here the brain. All right, now pay attention to the relative size of these because it'll give you a better idea of how much blood flow is going to each of these areas. So now if we go to exercise, we reduce not only the percentage but the amount. So notice how the size of this circle relative to the size of this circle. Okay, so it's a smaller amount and a smaller proportion. Heart gets more. It gets the same proportion, but 5% of 25 is more than 5% of 5. Kidneys reduce because we don't want to lose all of our fluid to the urinary system. But look at the brain. The brain, yes, we lose we have a smaller proportion of blood going to the brain, but these circles are essentially the same. Okay, and if you don't believe me, or if you think that they're a little bit different, 25 divided by 5 is 5, right? And 15 divided by 5 is 3. So you can see that they're pretty similar there in the actual amount of blood flow. But then where does most of the blood flow go? During heavy exercise, it goes to the muscles. Okay? And ultimately, this is determined by, well, what do the tissues need? So when I'm exercising, my intestines and stuff don't need a lot of oxygen, so we can reduce blood flow there. But my muscles, on the other hand, need a lot of blood flow, and so that's why we dilate those vessels and we send a lot of blood there. Okay, and this can happen via redistribution and or increased cardiac output. And so what we mean by redistribution is, well, we can constrict vessels that are going to places that don't need lots of oxygen, and we can dilate vessels that are going to places where we need lots of oxygen. And just like heart rate, there's intrinsic control of blood flow. So again, intrinsic control, that's coming from the vessels themselves. That's coming from within. Okay, so this is blood flow is changing because of things going on with the tissue. Generally speaking, if I increase metabolic activity, I have vasodilation. And then if I have decreased, I'll have vasoconstriction. So the way this works is a couple of ways. So we've got metabolic regulation. Okay, so if the vessels in your muscles, when you're exercising, need more oxygen. Well, and as a result of the activity, they're going to have high carbon dioxide, high hydrogen ion, high lactate. Any or all of these things will cause vasodilation. Okay. There's also what we call endothelial regulation. So this is the lining, the inside of the blood vessels. And so they release substances that cause vasodilation as well. All right. And then there's myogenic regulation. So hopefully you remember when we had talked about the urinary system, right? If those blood vessels start to stretch out, they can dilate, or if they're stretching out too much, will constrict. If they're not enough pressure, they'll dilate. It's the same type of idea. Okay. An example of some endothelial regulation, and this ties into what you guys did with lab, I believe, week 2, was where you're talking about flow. Okay. Blood vessels don't just line up nice and neat as they go through your blood vessels. They're bouncing off the walls and stuff. And the more bouncing off the walls, we call this shear stress, that causes blood vessels to release nitric oxide, and nitric oxide is a vasodilator. And so that allows blood to travel more easily through those blood vessels. So then we've got extrinsic control. And so these are the changes that are coming from somewhere other than the blood vessels. So this would be neural control. All right, as we've talked about in 220, and hopefully in your physiology class, if you didn't take 220, the sympathetic nervous system can cause vasoconstriction. Okay, it does this with epinephrine. Ironically, or interestingly, it actually causes vasodilation in coronary vessels. So, which makes sense. At a sympathetic response, I'm going to make sure I need to have more blood going to my heart so my heart can work harder. Okay, so what normally happens though is that this causes vasoconstriction. And so if I have high sympathetic activity, I actually cause vasoconstriction. Okay, remember epinephrine goes everywhere. Well, that would be a problem except for that we have that local control. So even though we might have a sympathetic response in our muscles, we can override that. Okay, and so what happens with the muscles, they're the ones doing the work. They need more oxygen. So this exercise stimulates that sympathetic response, which causes vasoconstriction, but we have to overcome this vasoconstriction. And we do this with the intrinsic control, but we're going to talk about this a little bit more later this week. So something to look forward to. So I guess that's what they call a hook or something in the media world. Anyway, so there you go.